Welcome to tutorial number 9. In today's tutorial, we're going to be covering how we can use the scikit-learn module in Python in order to create a random test set, as well as how stratified sampling works and how we can use scikit-learn in order to create a stratified sampling test set and a training set. Before we get into today's video, make sure you hit the subscribe button down below and like the video for more content just like this. And so in the last lesson, we discussed how we can use a hashing system in order to create a random test set and a random training set that can be updated in the future. Now, that was obviously a very good system, but in today's video, we're going to talk about how we can use stratified sampling in order to make sure that the data that we're using for our test set and for our training set is data that is representative of the overall training set. But before we do that, let's talk about how we can create a random test set using scikit-learn. So there's a function in the scikit-learn module called the train underscore test underscore split function. And what this function essentially does is it allows us to randomly select certain elements and push them into a training set and to a test set using a test ratio and also a random state. Now, the random state that we're going to be using is going to be 42. And this is just a randomly selected integer. You can select any integer you want. 42 is a typically selected integer, along with a test size that we substituted in right here. We said 0.2, sorry about that, 0.2 because we want our test set to be 20% and our training set to be 80% of the overall available data. And we're obviously going to pass in our housing pandas data frame object as well. And so you see here that we have some boilerplate code here at the top that just imports our modules as well as gets our data, reads our CSV file. But what this is going to do is it's going to return this random result here for us. So let's go ahead and print out our test set. And you can see here that for our test set, we got roughly around 4,000 rows using this function. So using this function, we were able to get 4,000 rows. And if we were to do our training set, we would get the complement of that. So we would get 20,000 minus 4,000, so roughly about 16,000 rows. And so you see that we passed in our housing data frame object the test size that we wanted. Now, if I made this, for example, let's say 0.3, we would expect that the test set would be roughly about 6,000 or 7,000, right? So here we got 6,000 rows in that case. So you can alter that depending on how big you want your test set to be. Also, we pass in a random state integer as well. It's just a random generator seed there as well. Okay, so you see how we were able to do that. This function will return basically two returns. It'll return a training set, and it'll return a test set as well. And you can get that there. Now, this system, remember, is just totally random. We're not considering any of the attributes inside each of the individual instances when we do this. So let's go down here to the bottom and let's talk about stratified sampling. So basically the idea behind stratified sampling is rather than simply taking this randomly, what we're going to do with stratified sampling is we're going to divide our data into homogeneous, mutually exclusive subgroups called strata. And so let's take, for example, our data, and let's try to understand our data in order to understand what are the subgroups that we can divide our data into. And so right here, I have a function here. And basically, remember this function, we talked about this before, and so I don't want to spend too much time on it. But basically, what it's doing is it's taking all of our housing data, which remember, let's go back to our housing data here. Our housing data had several characteristics, several factors, such as the housing median age, total rooms, total bedrooms, etc. And so basically, remember what it did was it created a histogram for each of these individual factors. So it created a histogram for the housing median age, a histogram for the total rooms, and it compared that to the total number of districts in the y-axis that exhibited that particular quality or that particular characteristic. And then you have the bins. Remember what bins is. Bins is basically the number of columns that you would have. So in this case, we're going to have 50 columns for each of our individual histograms. And then we have our fixed size, which just simply is the size of the histograms. All right. And so you see an X value and a Y value. And then we have the show function as well there. All right. Let's go ahead and run that. And remember, we already went through this before. So you should get a similar output. And it might take some time just to create the histograms. But let's go ahead and see. Yeah, okay, good. We got our histograms. So let's take a look at this histogram. Again, we went through this a couple tutorials ago. But let's take a look and zero in our on our housing median income or housing median income histogram. Remember what our y-axis represents. Our y-axis represents the number of districts that demonstrate X particular quality. So in this case, the quality that we're looking at, or the characteristic that we're looking at, is the median income. So in this case, what you can see here is that the median income is 0,246. It's separated by a number of 2. Remember that these median incomes are representing 10,000. All right. So you see here, this 2 here represents 20,000. The 4 represents 40,000. 6 represents 60,000, and so on and so forth. And so you see here, the number of districts that occur is the y-axis. So you see here that at roughly 40,000, you see a lot of homes, a lot of districts have a median income of 40,000, right? A lot of districts have a median income of 20,000. And so if you were to look at this graph, where is the majority of the districts? What is the median income of the majority of the districts? Well, you see here, it's roughly from 1.5 all the way up to about 6, right? You can maybe even argue up to 8 or 10. But for the most part, most districts, in most of the districts, the median income is 15,000, right? 1.5, all the way up to about 6, right? Which is be at 60,000. Now, keep in mind that this is data from the 1990s. And so because of that, median incomes were much lower back then. And now, of course, if it's adjusted for inflation, it might be different. But just in terms of raw numbers here, we're looking at most districts have a median income from 15,000 all the way up to about 60,000. And so you can look at some of the other data as well there. And let's take a look at some of the other data as well. Let's look at latitude and the number of districts. You can see here that many districts occur at a latitude of 34. So at a latitude of 34, you're seeing many districts, right? And so remember, our main idea here is like, where are housing prices going to give us the best ROI or the best return on investment? Well, if you're thinking about this, you would be looking at this and thinking, okay, we should probably invest in some area at a latitude of 34 degrees or something like that, right? Because there's more districts in that area. Okay, so that's something to consider. It's probably like an urban area or something like that. All right, so that might be important as well. Okay, so let's try to use actually get the data here using the pandas library as well as the numpy library. Okay, so basically what we're going to go ahead and do here is we're going to basically stratify this data into particular categories. So what we're going to go ahead and do is we're going to have categories from basically 0 to 1.5, 2 to 1.5, 3 to 4.5. Each of these are individual categories for our median income that we just went through. And for each of those categories, each of those closed intervals, we're going to have a particular number that's associated with a particular label. And so in this case, just take a look at the function that we have here. From 0 to 1.5, it's going to be 1. From 1.5 to 3, it's going to be 2. From 3.5 to 4, it's going to be 3. From 4.5 to 6, it's going to be 4. And then from 6 all the way to infinity, it's going to be 5. And in this case, we are creating a new column in our housing data frame object called income underscore cat. And what I'm going to go ahead and do first is I'm going to display the histogram for this, and then I'm going to run the housing underscore income underscore cat in order for us to see that data. Let's go ahead and run this now. And what you can see here is that when we run this, we see here that the houses here, you have roughly 1,000 districts where the median income is from 10,000 to 15,000. And then you have about 6,000 districts where the median income is from 15,000 all the way to going back here 3,000. And you can look at that so on and so forth, right? And so you see here how stratified sampling really allows us to break down our data into individual strata based on what we're observing. Now, you also see from 6 to infinity, you see here that those are people obviously on the higher income scale. You see here roughly around 2,200 districts have a median income of that. Those might be more rich areas as well, right? So you see how that data might, how we can display that data. Now let's go ahead and print the housing income underscore cat. Let's go ahead and print that out. And so let's go ahead and print that out there. We see how the data is being displayed. So you see here that for row 0, or for district number 0, I mean, technically it's not district number 0, but in our case, since we're considering this in terms of rows and things like that, we're going to give it 5. So that means is that in this particular district, in row number 0, so looking at that here, that would be like something like this probably. In row number 0, we see here that their median income is very high. It's like at 5. And then you see row number 1, row number 2, row number 3. It's assigning basically a label to each of these individual rows. And remember what these labels correspond to. The labels correspond to a particular bin closed interval. And so the 1 corresponds to $0 to $15,000. And so very few homes have that type of have that low of an income. Very few districts. And if you look at that right over here, you see very few districts less than 1,000 have a low median income like that. But you can see here the majority of homes, really, if you take a look at this, are anywhere from 2 all the way to 4, which 2 all the way to 4 would be something like 15,000 all the way to about 45,000, right? And so you see that there. Also, this NP.INF, basically that's meaning 60,000 all the way up to infinity, essentially. So basically anyone who makes $60,000 and above, right? And since there's very few people in that income category, we wouldn't say 60,000 to 70,000 or something like that. All right. And so you see that we have how we displayed that using the hist function, but we also saw that this housing income underscore cat is basically showing how this is like like a hash map, essentially showing how each of the districts correspond to a particular label, right? And now, considering this idea in mind, think about how we created our test set before. Before, we just created our test set using a random basis, essentially, right? But think about that. Let's say you were to do it randomly and you were to oversample, let's say, for some reason, by randomly doing it, you were to oversample from the people who make the people who make like 60,000 and above. Well, that's obviously the districts, at least, that make $60,000 or above. That obviously would not make sense, right? Because even if you were to do it randomly, we're not necessarily guaranteed that you would be sampling exactly, a majority of your samples, or a plurality rather, I should say, would be in the 30,000, or in this case 3 to 3 and up. 3 would correspond to 30,000 to 40,000, 45,000, right? We don't know that a plurality of your data sets, if you were to do it randomly, would be from 30,000 all the way to 45,000, right? We don't know that. And so doing it randomly might not be the best solution, right? It's kind of like now, if you were to do it randomly, take for example a coin flip. There is a law in probability called the law of large numbers that basically says that if you were to do a coin flip two times, let's say you both land on tails, that does not necessarily mean that there isn't a 50-50 probability that you would always land on tails, right? That wouldn't mean that that law would break. But if you roll a dice, or not, flip a coin, let's say 10,000 times, and you take a look at what are the chances in all those 10,000 times that you're either going to go tails or you're going to go heads, it would divide roughly to be 50,000, or 5,000, 5,000 on either side. It would go to 50,000, meaning that as you increase the number of instances of you doing a particular task that has a particular probability, the rate at which you are doing at the rate at which that particular task returns a true value or a false value will correspond to what the actual probability is, right? That's basically what the law of large numbers says. But in this case, we're only doing it one time, right? And we're using a random seed generator of 42. And so that wouldn't necessarily work in that particular instance, right? And so you'd have to consider that as well. And so what we need basically is we need a data that are in our test set that's going to be randomly sampled, but at the same time, it should be representative of these big income categories. That's what we want. And we saw here that the housing income cat gives us basically each row, and it's basically like a hash map, and it's showing what each of the median incomes would be, what at least the labels would be. And remember, each of these values, it's very important. These are simply labels that correspond to a continuous interval, right? The 5 does not mean 50,000. You should know that when we're covering this. 5 does not correspond to 50,000. 5 corresponds to 60,000 and above. That's what it corresponds to, because that's what its bin is, right? And so you see here, 2 does not correspond to 20,000. 2 corresponds to 15,000 to 30,000. And so you shouldn't get confused a little bit, okay? So how can we do this? How can we get a random test set? Well, there is a class called a Stratified Shuffle Split class in the scikit-learn library. And basically what this function allows us to do is it allows us to create training sets and test sets while preserving the distribution of the strata for an individual factor. Now, in this case, the individual factor that we've really been zeroing in on is the median income. And so let's try to create a test set considering only the median income and randomly selected there. Again, we are doing it randomly, but we are trying to you know, consider that as well. Consider this stratified sampling as well. Hence, we have a random seed generator of 42, right? Now, keep in mind that the random seed generator will always return the same numbers, right? It'll always return the same numbers. So the way you can think about it is it's randomly selecting it the first time, but every time after that, it's going to select the same data. Now, it's selecting the same data because the seed generator is going to return the same number every single time, just for our consistency. So keep that in mind there. Okay. Now, we typically pick 42. It's just a number that we typically pick. You can pick any number you want. All right. So let's see here. Let's go through some of the boilerplate code. So the boilerplate code here is the importation of the library as well as the particular class. And let's take a look at this. So we have split equals stratified shuffle split. And so here we're actually like creating the class here, and we're specifying some things to the class. We're saying that n underscore splits equals 1. Why are we saying n underscore splits equals 1? Well, because what we're saying is that we're going to split the data one time. We're going to split it into a training set, and we're going to split it into a test set. So we're going to have one split in the data. Into basically, we split it once, and we're going to get two sections, right? If we split something two times, we get four sections, right? So basically, it's a squared relationship, essentially. Not a squared relationship, but it's a double relationship, essentially, right? And then we have a test set that's 0.2. And then we have a random random seed generator that's 42. So we have that there. Next, we have here a for loop. Now, one of the things that you should know about a for loop is, typically speaking, like if you're doing Python coding if you're at least have done some Python coding in the past, you typically know that when you have a for loop, you typically loop through something like 10 times or 5 times. Typically speaking, when we're doing most of our machine learning here, typically speaking, we're only going to loop through the data actually one time. So we're going to use a for loop only to loop through the data just one time. And the reason why we're going to loop through it one time is because we're splitting the data one time, right? So that's what we have there. And so you see here that you have split.split housing, and then you're giving a housing income cat. So consider this like an X, and then consider this like a Y, essentially, is how you can consider that. So basically, we have housing, and what we're saying is that you need to split the data one time, right? And return a train index and a indexes, I guess you could say, right? While maintaining this particular distribution. Now, what's the distribution coming from? It's coming from here. This is the housing income cat, right? So basically, that's what it's doing. And it's going to get 20% of the data and return it as a test set for us. And it's going to return each of the indices, and then we're going to use the lock function, or the lock operator rather, and we're going to get all of the data using an array of indices. So let's go ahead and print out the test underscore indices. I always choose test just because it's like going to be fewer values, obviously. And so let's go ahead and return that there. So you see there that you got those particular indices. Now, those indices, remember, are going to be evenly distributed, right? They're going to be evenly distributed and be not evenly distributed. Sorry, I should rephrase that. It's going to be representative of this graph, essentially. It's going to be representative of these particular numbers. So basically, what we would expect is that the plurality, right, of these numbers, of these rows, would correspond to a a label of 3, right? 3 is the label from 3. So the plurality of these indices. And remember what these indices, because it can get confusing sometimes. What we're returning right here are the indices for our rows. These are the indices for the rows. Each row corresponds to a particular label. The labels here correspond to a particular continuous interval. So you need to understand that again. I'm going to say that again. Each of these numbers here are a row. They represent a row index. Again, as long as we have the indices, we can just use this lock operator in order to get our training set or tested. That doesn't matter. Our goal is the indices. Indices are what matter, right? Each of these numbers correspond to a particular index, to a particular row. The rows are labeled with a particular label, and those labels correspond to bins, and those bins are continuous intervals that represent the median income. You need to be able to understand them. Okay, so that's important there. And so you see that there. And so you see here, even you're seeing here, the labels here are 1 to 2. I believe this is actually a open interval. Actually, I think I'll check that later. But I think it's an open interval actually, because these are less than symbols. But you have an interval of 1 to 2, 2 to 3, 3 to 4, 4 to 5. You see that right there. Okay, so each of these indices are referred to the rows, and the rows are being given a particular label in this case. And these labels, these indices, if you were to add them up, right? If you were to not add them up, but if you were to basically say, I'm going to take the number of indices that have a label of 3, right? A label of 3, and I'm going to divide them by the number of rows that have a label of, let's say, 2. Which one would be bigger? Well, it would be the one with the label of 3, right? And so that's kind of the idea you should take. If I were to take these rows and I were to map them to their labels, and I were to take those labels and I were to say, count the number of rows that have a label of, let's say, 5, right? 5. It should be greater than the number of rows with a label of 1, because 1 corresponds to a closed interval between 0 and 1.5. And it's lower, right? The number of districts are lower, right? So that's important there as well. Okay, so try to understand that idea there. And then once we have those indices, again, we just use the lock operator here, and we just get the strata train set and the strata test set. All right. So now let's take a look at this at the very bottom here. I think we were able to get this video down to about 30 minutes or so. I don't want these videos. I hope these videos can only be about 30 minutes long. Now they might go beyond that, but if they're 30 minutes long, I feel like it's a good number in terms of how long these videos should be. But yeah, I think we're hitting about 30 minutes or so. So that's very good. But anyways, we have here strata underscore test set income cat dot value underscore counts. Okay. And it's dividing that by the length. Let's take a look at the return and then I'll explain it. So you see here that this is very representative of what we want. So you see here that 35% of the data. So 35% of the data, roughly, you can multiply each of these by 100 in order to get it to a percentage, right? 35% of the data, the plurality of the data is coming from a label of 3. And we would expect that, right? 35%. The next one is a label of 2. That's 31% of the data. You can see that it's right below that. So that makes sense, right? What about 4? You see 17% of the data is coming from 4. And that makes sense. Just taking a look at this graph and comparing it to everything else. Makes sense. Roughly 3.9% of the data is coming from 1. So that makes sense as well. 3.9%, roughly 4% there. Or 3.99, really 4%, I guess you could say, if you round that off. All right, so you see how it made a pretty representative sample. This is much better than a random result. If you were to just do this randomly, we might, if we were to do it randomly, we wouldn't get totally off numbers. We would get pretty, it wouldn't be so bad, but it wouldn't be as perfect as using a stratified sampling. Obviously, you guys should understand, right, that using stratified sampling would be much easier, much representative of the overall sample than just doing random sampling. Okay, and so let's go ahead and try to explain what this is doing. So let's go ahead and first of all, let's print this out here. Let's get rid of the value underscore counts. Okay, and let me comment that out over there. And let me just print that out. Okay, so I'm just printing out a section of it because it's good whenever you're doing this to just print out a section of it. So income underscore cat. So you see here, each of the rows are corresponding to a particular label. We said that before, right? And then what we're doing here, let me uncomment that. We're saying value underscore counts. So count the number of rows that have an index or a label rather of 5. Count the number of rows that have a label of 4. Count the number of rows that have a label of 3. Count the number of rows that have a label of 2, and so on and so forth for a label of 1, right? So basically what we're doing is we're counting the number of rows. Now don't get this confused. We're not adding the labels. That wouldn't make sense, right? we're counting the number of rows. We're not counting the row index, or else that wouldn't make sense, obviously, because just if a row was like at index 20,000, then it would outweigh a row at 5,000, even though the indices don't really matter at all. They're just used for our reference, right? We're counting the number of rows. Okay, so kind of consider it like this. Let's say you had 10 people, okay, and you ordered them from 1 to 10, 10, 1 to 10, and you said, if you're a person whose age is between 0 and 10, go at position number 10. If you're a person at if you're a person from age 10 to 20, go at position number 2, right? And so on and so forth. You would have to count the number of people, or the number of rows in this case. You wouldn't count the index that that person is at. You wouldn't consider the fact that he's in an index of 10. The indices don't matter at all, right? So you'd count the number of people who fall under a particular label. And so you'd count the number of people who have a label of 1, which would be 0 to 10. Or in this case, label of 1 would correspond to $0, making all the way up to $15,000, right? So you'd count that. That's what the value underscore counts does. And as it divides that by the total number of people, going back to my example that I just gave, the number of people who you're using in all of your experimental units. All right. So the number of people in everything. So in this case, in our case, it would be like what, 20,000, 4,000 for our test set. So again, when we uncomment that and just run it again, we see there that we get our distribution very nicely here, 0.35, 0.31, etc., etc. All right. So I hope this was helpful for you.